Welcome to our ME 452 final report covering the analysis and redesign of a prosthetic foot. My name is Scott.
My name is Eric Carter.
My name is Tadish DeBull.
I am Jeremy Turtle.
My name is Anthony Potajo.
For our product description, the function of a prosthetic foot is to give the amputee the ability to walk again. 1 degree of freedom for the foot can attach to the amputee's leg or prosthetic limb. Springs are added to encourage the natural movement and shock absorption. Also, no computers or electronics are needed to operate the foot. For our primary customers, we will use individuals requiring prosthetic foot post-amputation and individuals requiring upgrades to their existing prosthetic foot. For our secondary customers, we choose athletes that may need a prosthetic foot with added strength and durability. For production volume, we estimate 1,000 units per year, 800 to individuals and 200 to athletes. Here's an assembly view on the left and an exploded view on the right of our prosthetic foot, with each part labeled individually.
Functional analysis, the main goal is to replace the original foot. This can be done by first allowing motion by having the prosthetic foot support weight as well as support maneuverability. The second goal would be to minimize slip, which could be done by increasing the grip of the prosthetic foot as to clean the surfaces, as well as creating an ability for the prosthetic foot to be able to tolerate stress by distributing pressure on specific areas of the foot to hold weight and absorb shock in case a large amount of pressure was sent to the prosthetic foot all at once. The prosthetic foot should also be dependable by preventing wear and allowing the user to maintain control of the foot. This can be accomplished by minimizing vibration of the prosthetic foot and minimizing resistance the foot may have when the user interacts with the environment. The prosthetic foot should be able to ensure convenience by being easy to live with. It should make going about doing daily tasks simple and easy, such as if the person had never lost their foot to begin with. The prosthetic foot could be enhanced by adding comfort, and the prosthetic foot could be able to please the senses in the way that the foot interacts with the environment.
To determine the importance of each part in relation to the basic function of the prosthetic foot, a function component mapping matrix was created. The parts with the most X's, such as the keel, are important to the overall design of the prosthetic foot. However, parts with a low amount of X's are not as important and can potentially be redesigned, such as the ankle base and housings.
For the product family design, this is a list of our platforms and modules for both customer groups.
For our product family design, our primary and secondary product variants with the modules highlighted in pink show the components that can be switched out.
These are our platform and module divisions for the product family design.
For the part of the product family design, we highlighted in pink the common interface components that both product variants share.
Here, the product family assembly sequence for the prosthetic foot is shown. For this sequence, the two product variants represented by blue and red are differentiated on the 5th step when the pyramid adapter is introduced. This is relatively early in the assembly sequence, meaning that it can be redesigned. In the assembly sequence redesign is shown here. The pyramid adapter was moved to the end in order to delay differentiation until the 8th step so that for the first majority of the assembly sequence, the product variants are the same. An assembly analysis of the initial primary product variant was conducted in order to calculate the total assembly time and efficiency. The total assembly time came to be about 100 seconds with an assembly efficiency of 0.25.
For design for manual assembly design changes, we removed the screws that held together the pyramid frame with a pyramid adapter and replaced them with snap fits on the pyramid adapter and cutouts on the pyramid frame. We were able to improve assembly time at the cost of strength in the joint. For our next changes, we decided to combine the pyramid housing frame as one piece in order to reduce the part count.
For the redesigned prosthetic foot, another assembly analysis was performed. By reducing the number of parts by 2 and decreasing the insertion time of the pyramid adapter, we achieved a new assembly time of about 85 seconds, which is a 15% improvement. Additionally, the new assembly efficiency increased to 0.35, which is a 17% improvement from the initial design.
For our design and automated assembly design changes, we added flanges to the Dorsey and planter bushings to facilitate orientation. Other changes we made were chamfers added to the combined framed housing area to also add to easier orientation of the part.
The analysis of the pyramid frame subassembly before and after redesign is shown here. Initially, the total assembly cost was 5.25 cents, from which a large majority came from the insertion cost of that bushings. Additionally, the number of parts used is significantly larger than the theoretical minimum number of parts, increasing cost. With the design changes, we were able to reduce the total assembly cost to 3.21 cents, which is a 39% improvement.
We decided to process selection on the updated designs of the manual assembly components. The pyramid frame is made out of aluminum, which is a non-ferrous metal, and the shape is flatter folded. Based on that, the methods we had available were sheet forming, electromachining, and machining. Based on the mass and thickness, nothing was eliminated. For the tolerance, we chose 0.2 millimeters to ensure that the snap fit would correctly insert from the pyramid adapter on top of this, which did not eliminate anything. And then based on the roughness and economic batch size of 10,000, we were able to eliminate electromachining. This left sheet forming and machining, but based on the large economic batch size, since a blank could be created and then the cost could be amortized across all of the produced parts, we thought that would be cheaper than machining. For the pyramid adapter, we used ABS plastic and made it hollow to decrease the overall weight, which left us with machining, injection molding, blow molding, and rotational molding. The mass eliminated rotational molding, then the thickness did not eliminate anything. The tolerance is again 0.2 millimeters to ensure the snap fit fits in correctly, which eliminated blow molding. The roughness was lowered for this component because it might go directly onto the amputee's foot, which eliminated machining. And for the economic batch size, nothing was eliminated, so we used injection molding to produce this part.
Between die casting and injection molding, even with the changes made, we can save upwards of almost $3 per part.
After doing the DFMA process on the pyramid frame, we were able to reduce the cost of the part by 17% by eliminating extraneous slots in the sheet metal part and combining the pyramid frame with the pyramid housing. The most significant cost savings were realized in the die cost for the piercing step of the manufacturing process. Regarding the 3D hubs part estimate, the reason that the part is more expensive overall is likely due to the overhead required by 3D hubs themselves when they manufacture the part. Regardless of the slightly more expensive part cost through 3D hubs, the cost reduction was similar to that achieved through DFMA. In coming up with a product service system, we decided on creating a system that would allow the customer to easily return their worn-out keels for recycling. When the customer purchases the prosthetic, their information is recorded into an online database. Over time, the keel will succumb to wear from walking or running on it every day, and the customer can go online to order their replacement keel. The keel is then shipped from the manufacturer to the customer along with a shipping label that provides free postage to return the old, worn-out keel. When the manufacturer receives the keel, they recycle it and then provide a rebate to the customer to discount the cost they paid for the new keel. Then after the new keel begins to wear down, they can repeat the ordering and shipping process as many times as they need, as long as they are using the prosthetic. The justification for the product service system relies primarily on the environmental impact of the keel. Carbon fiber is not easily recyclable and is the part most susceptible to wear and tear in the product. By setting up a specialized carbon fiber recycling process, the manufacturer reduces their carbon footprint and costs for manufacturing future keels. The customer benefits from this process as well, given that they have an easy avenue for replacing the part of their prosthetic that wears down the quickest. The rebate incentive makes the customer more likely to return their old keel in order to save costs on the replacement of the keel, in addition to making the manufacturer more likely to retain the customer in the future, given that they would not need to replace their whole prosthetic after the keel inevitably begins to wear down.
In conclusion, the overall benefits gained from the redesign is that the total number of parts was reduced by 2, the assembly cost of the pyramid frame subassembly was reduced by 39% per unit, and there was an overall increase of 17% with regards to assembly efficiency. To self-critique our design, by redesigning the pyramid adapter to snap fit to the pyramid frame, the strength of the adapter was reduced, which was a trade-off for reducing the total assembly time. If we were to start over, we would approach this design differently by eliminating the screws and the ankle housing within the ankle-based subassembly, in addition to further optimizing other parts of the design overall to reduce assembly costs and time.
Thank you for participating in our presentation. Okay, that was